Welcome back to my series on essential skill number 1 for AP Chemistry, which is dimensional analysis and mole conversions. In this video, we're going to look at a common application of mole conversions, which is using them to help us find the empirical formula of a compound, and we'll also cover the related concept of molecular formula. So first, let's just go through kind of the definitions, what these two terms mean. So the molecular formula is just like the actual formula. It tells you how many atoms of each element are actually in a molecule of the compound in question. Whereas the empirical formula, it sometimes is the same as the molecular formula, but not necessarily. So it does not necessarily tell you exactly how many atoms are in a molecule, but it tells you the ratio of the atoms of each element, and it tells you it in the simplest form. Okay, so think of essentially like simplifying a fraction. The molecular formula may not necessarily be simplified, but the empirical formula always will be. So consider this molecule here. So to determine the molecular formula, we would just simply count up all of the atoms of each element in this molecule. So there's 2 carbons, there's 6 hydrogens. So the molecular formula is C2H6. Pretty straightforward. But the empirical formula would not be this, because these numbers are both divisible by 2. And so for the empirical formula, it needs to be simplified. So we would divide both subscripts by 2, and we would get CH3 or C1H3. We just don't usually write the 1. That would be our empirical formula. So it's pretty easy to find the empirical formula if you know the molecular formula, okay? However, more commonly, you're going to be asked to find the empirical formula a different way, okay? And we're going to cover that. And then if you could also imagine, if we knew the empirical formula, that is not enough information to determine the molecular formula. Because if the empirical formula is CH3, the molecular formula could also be CH3, could be C2H6, could be C3H9, etc. So we're going to look at the end how to determine the molecular formula if we know the empirical formula and one additional piece of information. So first, we're going to look at how to determine empirical formula. And typically in these problems, you are given the mass percents of each element to start. And that's how it's going to be in the example I'm going through in this video.
Okay, so these are our mass percents of the 3 elements, carbon, hydrogen, and oxygen in ascorbic acid.
And so if you're given the mass percents, the first thing you're going to do is consider that we have a 100 gram sample of the compound. Okay? Because, for example, in the example that we're doing here, it says it's 40.91% carbon by mass. Okay, well, if we had a 100 gram sample of the ascorbic acid and 40.91% of that is carbon, then that means there's 40.91 grams of carbon in that sample. So we need to get each of the elements into grams itself. So we simply consider a 100 gram sample, and then we can just convert the percents to grams without having to change any of the numbers. And of course, we don't necessarily know that we have a 100 gram sample, but as long as we apply this uniformly to all of the elements, it's fine. You could even pick a number other than 100 if you want. It doesn't really matter. It's just 100 is the easiest because the numbers will not change.
So the first step, we assume a 100 gram sample. And so because of that, in that 100 gram sample, the grams of each element are just the same as the percents. So if we have a 100 gram sample and 40.91% of it is carbon, then we have 40.91 grams of carbon in that 100 gram sample. And we have 4.58 grams of hydrogen in that 100 gram sample. And we have 54.51 grams of oxygen in that 100 gram sample. And again, even though we don't necessarily have a 100 gram sample, it's fine because I applied it the same way to all of the elements in the compound.
So once we have the grams of each element, the next step is going to be converting grams to moles, doing a mole conversion using the molar mass.
So the next step, we're going to convert the grams to moles of each. So if you remember from the mole conversions, we can convert from grams to moles or moles to grams using molar mass. Since we're starting with grams, we're going to want to put grams on the bottom to cancel it, moles on top, and the conversion rate is that 1 mole is equal to whatever the molar mass of the element is in grams. Molar mass of carbon is 12.01. Hydrogen here, same setup, grams on the bottom, 1 mole on top, and then the molar mass of hydrogen is 1.008. And then oxygen, same setup, 1 mole on top, grams on the bottom, molar mass of oxygen is 16.00. Okay, so we're going to go ahead and calculate each of those. We're dividing by the molar masses since they're on the bottom. So we have about 3.406 moles of carbon. Don't round too much at this stage. I mean, technically here 4 sig figs is correct. This number has 4 sig figs, this number has 4 sig figs. So keeping 4 sig figs is good. You could even keep more if you want. Sig figs aren't that important in these problems, but just don't round too much because that can lead to rounding error. So for hydrogen, we're going to get 4.544, I'm going to say. And then for oxygen, we are going to get 3.407 about. Okay, so we've calculated the moles of each element in a 100-gram sample of ascorbic acid.
Once we have the moles of each element, what we're going to do is we're going to divide all of them by whatever the smallest number of moles is, okay? And when we do this, the hope is that we'll get whole numbers, okay? But it won't necessarily always come out perfectly cleanly. So if you're within 0.05 of a whole number, you can round to the nearest whole number. Maybe even a little bit more wiggle room than that, but definitely within 0.05 of a whole number, you can round to the nearest whole number, okay? If you're not, what you want to look for is kind of being near a decimal that's like a clean fraction, okay? So like 0.5 would be 1/2, 0.33 would be 1/3, 0.67 would be 2/3, etc. So you want to look for something like that, and then you're going to ask yourself, what's the smallest integer I would have to multiply this by to make it a whole number, okay? And then whatever that is, you would have to multiply all of the elements by that, even if the other ones were whole numbers to start with, just because you can't just multiply one without multiplying the others. You have to apply it uniformly.
Now we're going to divide them all by the smallest number. So what's the smallest number of these? Well, 3.406. So we're going to divide all of these by 3.406. So this is obviously just going to be 1. This one is going to be 1.33, 0.334 if we keep 4 sig figs. And this one looks like that's going to be about 1, but yeah, pretty much exactly 1. You know, even if you're getting like 1.0, Even if you got 1.01, which it's even closer to 1 than that, but even if you got that, that's close enough to round to 1 as long as it's within 0.05. So that one we can go ahead and round to 1. This one, though, is not close enough to round to 1. It is not within 0.05. So the next thing we want to think about then is, well, if it's not close enough to round to a whole number, then we're going to need to multiply it by something to make it a whole number. So what's the smallest integer we would need to multiply this by to make it a whole number? Easiest way to figure that out is ask yourself, is this close to like a clean fraction? And this is approximately 1 1/3. Okay, 1 1/3 would be 1.3 repeating. Okay, so then we would need to multiply by whatever's in the denominator of that fraction by 3. Okay, and when we do that, I mean, you could just plug this in the calculator, but you can also just think about it, well, 1 1/3, that's 4/3 if we write it as a single fraction. So 4/3 times 3, that's going to be 4. Okay, so that makes this a whole number now. Okay, these are already whole numbers, but if we multiply this one by 3, we have to multiply them all by 3. So 1 times 3 is 3, 1 times 3 is 3, and once they're all whole numbers, we can go ahead and write our empirical formula. Those whole numbers just represent the subscripts. So our empirical formula is C3H4O3.
Okay, now once we know the empirical formula, again, that itself is not enough information to determine the molecular formula. But if we know the empirical formula and we know the total molar mass of the compound, we can determine the molecular formula. And the first step for doing that would be to calculate the molar mass of the empirical formula. Okay, so the molar mass they give you in this problem, that's the actual molar mass of the whole compound or of the molecular formula. But we know the formula of the empirical formula, so we can use the periodic table to calculate its molar mass. So we're going to do that.
Now that we know our empirical formula, and we also know the molar mass of the compound, we can go ahead and determine the molecular formula. So first thing we're going to do this is calculate the molar mass of the empirical formula. So C3H4O3, the molar mass of that. Well, that's going to be 3 times 12.01 plus 4 times 1.008 plus 3 times 16. That's going to give us 88.062.
And then we're going to divide the molar mass of the whole compound over the molar mass of the empirical formula. And when you do this, you should get a whole number, or very close to a whole number that you can round to the nearest whole number. This one should not give you with the empirical formula, sometimes you got the fraction thing, and then you had to multiply it by an integer to make it a whole number. That should not happen here. It should come out to be a whole number or very close. So if it doesn't, then you probably did something wrong along the way.
And then what we're going to do is we're going to take this molar mass that they give us for the overall compound, and we're going to put that over the molar mass of the empirical formula that we just calculated. And when you do this, this should always give you a whole number, or at least close enough to a whole number to be able to round to 1. So in this case, we get exactly 2. Okay. Again, it might not be exact. I mean, in theory, it should be exact, but just due to, rounding, whatever, it may not always be perfectly exact, but it should always be close enough to a whole number.
And then whatever that whole number is in step 2, that tells you what it's basically the factor by which you have to multiply all of the subscripts in the empirical formula to get to the molecular formula.
And whatever that whole number that you get is, that just tells you the factor by which you need to multiply each of the subscripts of the empirical formula to get the molecular formula. So we're going to say C 3 times 2 is 6, H 4 times 2 is 8, and then O 3 times 2 is also 6. So that is our molecular formula of ascorbic acid.